Hi again, this is Claudio from expertfa.com, recording for you the 5th webinar meant to help you improve your finite element analysis skills and also Ansys Workbench skills. Firstly, I would like to invite you on our webpage, expertfa.com, which is updated very often and contains lots of hands-on tutorials. Also various and advanced solved FEA scenarios on the gallery page. Also, we invite you to check our book. Our webinars page. And of course the contact page. Also, feel free to visit our YouTube channel. Where lots of videos can help you with ideas and hints regarding your FEA research and work. So, today's FEA exercise will be a drop test of a jello material, a very soft rubber material. We have opened an explicit dynamics analysis and it's time to define the rubber-like material. So let us go to engineering data sources, and from here we will select hyperelastic materials. As you can see, the given samples are, let's say, result from experimental data. But for today's webinar we do not have such data, so it is very convenient just to duplicate our default material. We will rename it simply rubber, and from here we will change the density the Poisson ratio, and the Young modulus we will calculate it as follows. So as you can see, in our material we need the Young modulus, but soft materials as elastocil, let's say rubbers, only provide the shore hardness. I'd like to find an elastomer datasheet in order for you to see the usual properties. So So I think this is what we need, yes. Let us select the softest, let's say, rubber-like material, 13 on shore hardness. Ansys doesn't work with shore hardness, so it's just logical that we need some kind of a conversion. Shore hardness conversion to Young modulus. So, Mr. Bill Royce from 3D Vision developed a formula that can help us make such a conversion, shore A to Young modulus. What we need is to open an Excel spreadsheet and insert the formula there. Let's copy the formula. And we need to replace the shore A durometer with our shore hardness that we found in the datasheet. So 13 shore A hardness equals to 0.715 megapascals. This value we will copy it in our properties. So our material is now completely defined. Just to remember, we can specify the amount of Young modulus here. What we need now is to import our geometry and double-click model. And hopefully the mechanical window will open. If not, let's double click again. Now the geometry is being imported. For our rubber material, we need to assign it the proper, let's say, material. The mesh, let's make it very coarse, -100 relevance. And regarding the sizing, we'll make the smoothing as low. Let's generate the mesh. And the statistics show a very good mesh. So we will let the FEA run for half a second, and we need to define the gravity direction. This means we will apply a coordinate system on this face, and let's say the x-axis, we will define it by geometry selection and select this edge. So it's oriented, let's say, on the negative side of the x-axis. Let's go to Explicit Dynamics and assign standard Earth gravity. We choose our new coordinate system, and the direction will be the negative side. So as you can see, there is a yellow arrow that is pointing downwards. So let us fix the bottom face of this metallic plate. And we will ask for a directional deformation along x-axis, but on our coordinate system. Also the directional velocity on the same axis. And the stress in all the parts. So this should be all. Let us solve this FEA. Clicking on solution information, we will see what the solver is doing. The FEA will be done in 90 minutes. Meanwhile, we can look on the, let's say, energy conservation and see that the energy error is constant, almost zero. So for the moment I will interrupt the recording and come back when the FEA is finished in 19 minutes. So the FEA is finished now. It takes some time to expose the results. Instead of 90 minutes, it took 45, as we see on the elapsed runtime. What I wanted to show you is if you multiply the number of cycles with the time increment, you will get the end time. So 1233017 multiplied with 4.055 divided with so it's 0.5 seconds. Finally, the FEA finished. Let's animate the results. So this is what happens for 0.5 seconds with this rubber cube. So let's now check the velocity of the cube. With the normal peak when it touches the edges. And the strain in the cube. Also, let's check the stress. So, let us see what happens when we prescribe an even softer material. This meaning, let's duplicate this FEA. We will change, and instead of Young modulus equal with 0.715 megapascal, we will insert 0.01 megapascal. Let's make the modification here is 0.01 megapascal. We'll close and double click the model. On model, let's right click and refresh materials. Let us save as webinar 5. And let us solve. If we click on solution information, we will see how much the FEA takes to finish, 22 minutes, but in reality it will be around 50 or 60 minutes. So I will pause the recording until the FEA is finished. So the second FEA just finished, and we will see the result animations. This was the vertical displacement. Here is the vertical velocity. The strain. and stress. So this is all for today, and for more advanced FEA we invite you to access our tutorials and gallery page from expertfea.com. Have a nice day and all the best.